Today's speaker, the first outside speaker we've had, Paul Kwiat of University of Illinois, Urbana-Champaign. His background is quite a remarkable rise. Got his PhD at Berkeley some years ago. And he's been doing non-classical effects since day one. He spent 2 years as a Lisa Meitner Fellow in the group of Anton Zeilinger. Then went on to Los Alamos, where he was an Oppenheimer Fellow. And he was also awarded an NRC postdoctoral fellowship, but decided to take the Oppenheimer. There's more money and anyway.
I jilted him.
That's the best one that got away. And he's a fellow of the Optical Society and APS. Invented the first two sources of polarization entangled photons via down conversion, and has used it for numerous quantum experiments. He joined the faculty at Illinois in 2001 as the Bardeen Chair. He was awarded numerous prizes, including the OSA's R.W. Wood Prize, and if you don't know who R.W. Wood is, you should go check that out. And has written nearly 200 publications.
Oh, I didn't write any of them.
Yeah, okay. And
it's Michelle Obama. I just copied him.
Yeah, okay. And today he's going to tell us about quantum communication, and hopefully he promised me he wouldn't drone on too long.
So that's an inside joke that you'll get in just a moment. So thanks so much for the invitation, and thank you for everyone for showing up. I guess it was pizza for lunch today. Is that the thing? Lots of good stuff. So I always change my title a little bit, at least. So this is a little bit too general. So I'm going to narrow it down to advanced free space quantum communication, and just talk about some of the things we've been working on at Illinois for the past couple of years. This is two projects mostly. One which is funded by the Navy and one which is funded by NASA. And I have a host of collaborators helping with these projects, and I'll try to indicate where the Duke and Ohio State are for this Navy project, and to the right-hand side, JPL and the unfortunately named ISIS. That's Herb Bernstein was a theoretician who came up with the main project for this. Okay, so I'm going to start with a bit of shameless advertising. If any of you are ever out in Champaign, Urbana, we have an outreach activity. I run the world's only science-based escape room. Solving the mystery of missing quantum physicist Alberta Schrödinger, who's working on a room temperature quantum computer, and enemy agents are after her, and she disappeared, and so did our own agents. So you can come and try your hand at that. And we've been running for about 2 years now. And we've had actually close to 4,000 agents now. And in fact, in this past August, we went to the AAPT, American Association of Physics Teachers meeting in Washington. And we had kind of a local room. And in 3 days, we ran 187 agents through. And in fact, including 3 agents that are in the audience right here. And I won't say how they did. OK, I'll just say that science saved the day. OK, so. If any of you have, so this actually was wildly successful. I was super happy, and in fact, we were invited to come out to the March meeting, which we will do in Boston. So if any of you guys are going out for the March meeting, make sure to sign up for LabEscape and see how you go. Okay, so these are my own agents, and these are the people who are mostly associated with the projects that I'm going to talk about today. Mostly. Joseph Chapman and Alex Hill, with other help from a couple other graduate students, Dalton, Chris Zeitler, and Christina Meyer. And we're always on the lookout for other people, so please talk to me if you're interested in that. And finally, the university is seeking more senior agents. In particular, we're having faculty hires this year, both in physics for experimental quantum information and also in computer science. So ads for that will appear soon, but if you're interested in knowing more, please talk to me. OK, so this is the outline of what I want to talk about today. Normally, when people go through these things, they put in gray the things that they've already talked about. So I have my first thing kind of already in gray, because I'm going to go just very quickly over quantum cryptography, because this is a seminar, so I'm presuming that most people have know what the basic idea is. And then quickly move into why we might want to go away from fibers into free space, where the regimes of that are. And that leads into our mobile platform, quantum key distribution, and then kind of change gears, moving to much longer distances into space, and the experiment we've been working on, some of the challenges with that, and what that might lead to in the long run. OK, so I do encourage you, if you have questions, please ask them as we go. I'd love to be interrupted politely, please. OK, so of course, with encryption, the idea is we want to have a secret message between two players, say Alice and Bob. And in quantum cryptography, we're going to achieve that by distributing a random key, which is just a string of zeros and ones to these two parties. No one else should know what that key is. And then that key can be used either to do bit-by-bit encryption, so-called one-time pad, or we can use that key as a seed to generate a much longer string that we can then use in this sort of encryption. So we will use single photons, the quantum states of single photons, to encode this information in a way that we can detect any eavesdropper. So in order to make such a system, we need single photon sources. I say ish, because if you had single photon sources, great, but you can also use attenuated coherent states, like a weak pulse laser. Entangled photons are also very good for this. OK, we need some sort of states that we can use to encode zeros or ones. So for example, polarization, I'll be talking quite a bit about. And we need some way of detecting those photons. OK, so that's not quite enough, because if we just use this, then if I had an eavesdropper in the middle, she could make a measurement of any photon going between Alice and Bob. She could determine what the polarization was, send along an equivalent photon onto Bob, and she would get information, but she wouldn't be detected. So to detect her, we're going to need to also send in a basis that's a superposition of this data basis, and that will allow us to confirm that there's no eavesdropping, because the eavesdropper won't know which photons are encoded in the horizontal vertical basis and which in the superposition basis. So when she makes measurements, she will introduce errors sometimes. OK, so obviously, for those of you who know QKD in more detail, there's kind of a lot more to the story, and you have to do error correction and privacy amplification and things, but I'm going to leave that all aside. And let's just talk about sort of the two main avenues that we have for doing this, which is either going through optical fibers or going through free space. And then depending, that fiber could be its own sole fiber, or it could be part of a network, although this is more challenging, because you have to make sure that you have a direct fiber link. And in free space, of course, we can also run either at night or day. I should say there's almost another category here, because I did see recently a paper talking about trying to do optical communication underwater, so quantum communication underwater. And they were able to do quantum encryption over something like 1 meter or 2 meters. I don't know exactly why that's that useful, but anyway, it's could be another venue. OK, so there have been a lot. Quantum cryptography, the BB84, this is Bennett Broussard in 1984, so obviously it's been around for quite a while. And there are now commercial systems, for example, that you can get in fibers. For example, ID Quantique is one of the main companies selling this. This is in Switzerland. And already a decade ago, they were used to secure some elections in Geneva, and then secure the World Cup. And there's a network in Tokyo that's been set up. It's been used for some bank transactions. So there's been a lot of other applications of this. I'm certainly not going to go through all those. Maybe more interestingly, in China now there's a link, a multi-node link connecting Shanghai to Beijing, trying to do quantum encryption. And I heard someone say that China claimed that by 2025 or something like that, all of their main messages would be quantum encrypted. OK, I have no idea if that's true, but it's a claim that at least they're thinking in that direction. Okay, but nevertheless, there can be problems. Yes?
So what do they mean by a trusted node?
A trusted node means that the signal here is received and then measured by a classical detector, and then we send on again. So it's an actual, I'm not allowed to have an eavesdropper at that node. The eavesdropper can only be on the intervening stations. So maybe there's a security guard standing there whom you trust. And I'll talk a little bit more about the protocol later on, how that works. Okay, so problems with fiber. Well, basically you need to have a direct optical path, or you need to have these trusted nodes, because you can't do a conversion. For example, you can't just put a normal, if you put a detector in, you will have collapsed the quantum state by measuring the photon. So the other problem, of course, is that the transmission is going to drop exponentially over length. So a typical telecom fiber might have a loss of 0.2 dB per kilometer. Over 200 kilometers, that corresponds to a transmission of about 10 to the minus 5. If instead you want to go 1,000 kilometers, of course, that doesn't mean that I just have to divide this by 5. I have to take the fifth power of that, so I get a transmission of 10 to the minus 25, which basically means that you get absolutely no signal in this case, because you're trying to send single photons one at a time. You can do things with quantum repeaters in principle to make a link that is secure, and hopefully someday we will have such things, but we certainly don't have them yet. And the other disadvantage of fibers, or one other disadvantage for fibers, there are certain applications. For example, you want to go into space, or you want to go across water, or maybe you're on a battlefield and you're just not going to have fibers there. Okay, so this is going to lead us then to think about free space channels. Yes?
Right, so can I think about attenuation in optical fiber, just a non-unitary transformation that removes probability amplitude from the photon state that we send at one side?
Yes. Perfect. If you want, I can repeat that to everyone, but he just said, is it basically just a lossy element, non-unitary loss of amplitude, and yes, that's perfectly fine. Fibers can do other things. They can also scramble polarization and do other bad things, but in terms of loss, that's all I want. So as far as I know, this is still the world record terrestrial free space quantum key distribution record between two of the Canary Islands for 144 kilometers. These are systems where I have telescopes on each of these islands, and they're somewhat unique in that the telescopes can point horizontally. Most telescopes, when they're made, are not actually designed to point horizontally, because why would you ever want to? You certainly don't want to try and look at the stars through all the turbulence of the atmosphere. But anyway, some of them can. And they're pretty high up, which actually makes their life quite a bit easier, because they don't have to deal with turbulence as much. And they also use this to do teleportation of the state of a photon between the islands, and that was at one point the world record. We'll come back to that in a little bit. Okay, so now, pardon?
What's the number again, the record?
144 kilometers, which is just the distance between these two. So several years ago, there was a call from the Navy where they wanted to develop ship-to-ship quantum cryptography, and we were given the task of trying to come up with systems, investigate systems that could go between ships separated by 30 kilometers up to, say, 100 megabits a second. And the program manager at that time, Carrie Schwartz, said, and I wanted to work in all weather conditions. I added that to this slide this particular weekend, because probably not so easy to do quantum cryptography during a hurricane or other bad weather conditions, so that was maybe completely unrealistic. But nevertheless, this was the task that we were given, and I'm part of a team that includes Ohio State and Duke and Boston University and University of Arizona. So the idea is that we want to be able to do, say, ship-to-ship communication. And one can ask, well, what problems might we imagine would arise in this sort of an application that wouldn't have arisen in other applications that had been looked at so far? This is part of the audience participation part of our show. Why is this not necessarily that easy?
Is it because the ships are moving?
So that's one thing, which is that the ships might be swaying a little bit, and that could be changing the basis if you're using polarization. Although you can partly get around that if you use, say, circular, right and left circular to do your data encoding. That helps somewhat. What else?
You can't really shoot a free space trajectory like without any interference from other objects flying through the path.
So in particular, other objects. And what is the main object if you have two ships that are far away from each other?
Here.
The The ocean. The ocean is the object that you get into trouble with. So in particular, if I have two ships here and their mass are 20 meters up, and you just draw a straight line between them, you come very close to skimming the surface of the water. And when you get close to the surface of the water, there's a lot of aerosols. And in particular, the turbulence above the water gets particularly bad. So the CN squared, that is a measure of the turbulence. I don't want to go into exactly what that means, but let's just say big numbers are bad, small numbers are good. So bad is up and good is low here. And this is showing, plotting what the CN squared is under some simulation, depending on what the starting height is as a function of the distance out to 30 kilometers. And you see that if we start at 20 meters, the turbulence gets really bad. That's when we're skimming right across the surface. And if instead we could go up to 50 meters, then the turbulence is actually reduced by almost 2 orders of magnitude. So that can be extremely helpful. And so our approach to this then is that we're trying to develop a drone-based system where we would send the drones up between the two ships, and they would have their quantum communication between them, and then they'd come back down. So these are, in some sense, it kind of depends how this is done, but you might say that these are trusted nodes. But on the other hand, they're just going straight above the ship that you're in, and you can just watch them and see if anyone flies up to them. And the design is that there's no other way to control what's going on with the drone other than actually being there with the hardware. OK, so that's the assumption. There are other ways of doing this where you have a tether going up that you could fix that. Yes?
Are they like physically wired to your ship, or are they sort of remote?
Well, there are two different ways you could imagine doing this. One, which is that they're really not attached at all, in which case they have a battery on them to fly. And that's everything I'll be showing you is with a battery, although we're now trying to develop a tether system just so that you can stay in the air longer.
What is the horizontal axis of that graph?
Oh, this is the distance between, this is the turbulence as a function of where you are along this trajectory. The distance starting out at one of the two ships and then going over to the other of the ship. I mean, it doesn't necessarily involve a ship. It's just the turbulence along this path. So you start out with an altitude that's, say, 20 kilometers, and then here it gets to like 20 meters, and then here it gets to like a half a meter, and then it goes back up to 20 meters. That's why the turbulence gets worse in the middle. Other questions? Thank you so much for the, yes?
So can we correct these errors due to turbulence in principles analogous to, say, adaptive optics or something?
You can certainly use adaptive optics, which help in terms of collection, but then you might also need to have a very big collector, which is not necessarily that easy to do. And certainly if you have lots of aerosols, adaptive optics, which you do right near the surface of the water, those scatter the photons. So adaptive optics doesn't really help in that case. OK. So we've been trying to make such a system using these octocopter drones, so-called DJI S1000. So we have, I don't know that I want to go over this too much in detail, but basically we have classical communication and also quantum communication going between the two drones. And there is as I'll say, we have a classical beacon to help with stabilization, and then there's a wireless link that connects them. And then they also have to know where they are, and if we're indoors, we do that using the so-called Vicon motion capture, basically where you put a couple ping pong balls on top of the thing, and then they have cameras in the room that monitors where those ping pong balls are. You might have seen this, for example, they use this in special effects in movies where they're trying to convert an actor's motion into a computer-generated actor or something like that. And then outdoors, we can use a GPS RTK system it's sort of like GPS, but there's an extra ground receiver that gives you a little bit more resolution. So one of the main difficulties, and this is one of the main things we've been working on for about the past year, is to try and come up with a nice pointing and tracking system that enables you to do this. And so the way that we do that is we have beacons on each of the drones. So our sending is actually done at 650 nanometers, but we're doing the alignment. On one drone, we have a 710 nanometer laser beam, which comes out through the same mirrors that the quantum source would go, and then makes its way to the other drone. There's a dichroic mirror that pulls off this alignment laser, and then it goes to a quad cell, which is basically 4 detectors, and you take the difference between left and right and the difference between top and bottom, and that lets you know whether or not you're centered. And that error signal then gets sent back by a low latency wireless link that then adjusts these steering mirrors to try and keep this locked on. And similarly, the receiving drone also has its own alignment laser that comes back to a quad cell on the transmitting drone. So there's wireless link going both ways. OK. Yes?
Is the light source mounted on the drone?
The light source is mounted on a gimbal under the drone, so that can move around a little bit. It's helpful for keeping it stabilized. So one of the challenges, so people have done some other free space things. So in particular, Thomas Yenevine had an experiment about a year ago where they went from a plane to a ground station, and they were able to do some quantum cryptography. But the plane can carry much bigger stuff. And the drone can carry something like 11 kilograms of extra weight in addition to its own, which is already a lot. It's a pretty, because it's a pretty big drone. But that starts to disappear pretty quickly when you start putting all of these optics in. So one of the things we've been doing is replacing a lot of things that we can with 3D printed parts. So that makes them quite a bit lighter. So we've been able to save a kilogram, something like that. So here's what the transmitter would look like. So the light sources are coupled by fibers. And we start out with, say, vertically polarized light here. So let's see, I'm going to start with this one. Horizontally polarized light is converted to right circular, and vertical is converted to left circular. And then over here to check, I'm going to use linear polarization horizontal. So I'll encode the data in right and left, and then I'll check with linear polarization to see if there's an eavesdropper. OK, so this is some data showing if we have a flying transmitter and a stationary receiver. This is if we don't have any optical stabilization on, basically we don't get any signal through at all. And if we do have our locking system on, then we're able to get stable locks for over a minute. We don't really have anything much more than a minute because it's heavy enough that we've run down our batteries, which normally can run up to 15 minutes, but they only go up for about 2 minutes, and then they're out of battery, and then it comes back down again. So that's why we're pursuing a tether, because then we can stay up arbitrarily long amounts of time. This is over a 5-meter link, so this was done indoors. And if we just take this loss here, this 10 dB loss, and we were running at 200 megahertz with about a 0.1 photon per pulse, then that would correspond to something like a 6 megabit key after about 100 seconds of data. I should say we don't have a full quantum key distribution system working, so this is just estimated numbers. We have, over the summer, moved to being outdoors. And I have a lovely little movie showing that here. It's kind of fun, if I can get it to go. And I hooked into surround sound for this, so we can you can experience what this is. Oh, no. Did it lock? Let's try that again. So I'm going to call your attention to these trees, actually. Because the trees initially aren't really waving around a lot. And now that the drones are in the air, the trees are actually waving quite a bit. So I don't know that you could really call this stealth communication, because they're really pretty loud, obviously. And in fact, it's quite difficult to run both of them indoors in the same room. There's a robotics room for flying drones at the university, but when you can't really put 2 of these in the room at once, because the turbulence from one of them really destabilizes the other one, so it's really quite difficult to run both of them in the same space.
So how resilient would they be to inclement weather?
That's a good question. I'm going to say I don't know the answer to that yet. At the moment, we're just still trying to get things locked, and I think we're very close to that. We've made some recent improvements. One of the things is trying to get a very low latency. You can't use standard wireless very easily, because wireless, although it can have a very high bandwidth, it's designed to send in big chunks, not little chunks with very low latency. And if we're trying to do optical feedback, what we want is just a small amount of information, but coming very soon. So we've been developing some software-defined radio, which should get around that problem.
Are you saying that the drone was blowing the tree? Or is that a joke?
I think it is. I can't verify that, but I think that that's true. Because they're pretty close to the trees, and when the drones aren't up, they're not really moving very much. And when the drones are up, it looks like they're moving around a lot more. OK. That's how we get wind, right? The trees make the wind by moving, yeah? OK, yeah?
Sorry, the previous slide mentioned this loss of power by decibels. So is your statement that the amount of information you can transfer goes down because of this loss factor?
Yes.
Is that because the photons are missing the other drone, or what?
Yes.
Right. Because if there's just a non-unitary decrease in amplitude, you should still get the signal out anyway.
You have to catch the single photon. If you don't receive the single photon at the end, it never becomes part of the key.
I see, but even if the photon attenuates and you still reach it, you can still get that data out, even if the amplitude climbs.
If it makes it, then you can still get it. So you can still do quantum key distribution, although there's a limit to that because the noise on your detectors is constant. And so as the signal goes down, the signal to noise ratio is also going down. And if that gets to a low enough value, then you can't ever do secure quantum key distribution.
You're just completely missing the detector here. That's what's going on.
Correct. Yep. Okay, so another challenge here, and this is what my colleague Dan Gauthier at OSU has been working on, is developing the source. You need to eliminate side channels. So in particular, it's not going to work. I mentioned that we have these 3 separate sources. And it's not going to work if, for example, they each have a slightly different color, because it would be in principle possible for an eavesdropper to measure the color without measuring the polarization. So the eavesdropper would get complete information about which polarization it was, but will not have changed the polarization by measuring it. She only has to measure the color. So, or some other degree of freedom. So one partial solution to that, we're doing this with these LEDs. But normally LEDs, it's very difficult to turn on and off an LED very quickly. So these are so-called resonant cavity LEDs. They have a cavity around them that allows you to switch them on a nanosecond timescale. And they're also quite broadband. So this is what the 3 LEDs look like with they're not filtered. So they have a bandwidth of roughly 10 nanometers. And then we can simply pass all of them through a single narrowband filter. And then they have the same spectrum. You still have to be able to match the temporal waveform. And so Dan Gauthier is doing that with an FPGA, and they can match that pretty well to within something like the 100 picosecond level. And so if you make the pulses a couple nanoseconds long, that 100 picosecond level is not leaking too much information. But this is a serious problem that plagues any implementation that uses multiple lasers, which is most implementations, or at least many of the implementations have this. And most papers don't talk about this as a problem, but it is one. And that's why if you can do this with entanglement, which is the eventual goal, then that solves that problem altogether. OK, so I'm just going to show a few estimates of the what we might be able to get out of this kind of system as a function of channel length. And depending on what kind of error rates we have in the system, and then also depending on how big the optics, the transmission and the collection optics are. Not surprisingly, if you go to bigger collection optics, you get more key through. So this is saying that if we were counting for 100 seconds and we were running at 200 megahertz, and we had, in this case, 0.01 mean photon number and timing resolution of a few nanoseconds, and we're assuming that there's 50,000 counts per second background, and that the drones were completely tracking each other perfectly, this is what we could estimate for about how far we'd be able to go. So something on the order of between 500 meters and 1,000 meters. Now, you might say, well, just make a bigger collector. And certainly if you go to a bigger collector, though, and you try and do that with a lens, it gets very heavy. So that's not going to work very well. So one of the things we're trying to develop now is something with reflective optics, which could be much lighter. And if we can get, say, a 10-inch collector there, then we should be able to go out to something maybe like 5 kilometers of that order. OK, again, this does assume that we have perfect tracking, which we don't in practice at the moment. So where we'd like to go with this, or why I think that this is interesting, is that this does have the possibility of then having a reconfigurable network where, for example, if something happens to one of your parties, you can shift one of the other drones along to take its place. Or if there's something that is in the way, for example, you can just reroute around relatively easily. So I guess one of the reasons I'm particularly interested in this is that this could be somewhat enabling for making quantum cryptography much more widely accessible. So the US is not all that interested in quantum cryptography, it turns out, in terms of the government. I'm not speaking personally, but in terms of the government. But many, basically lots, everyone else is, I'll say. Lots of other countries are. And one of the difficulties with quantum cryptography is that, for example, you don't have a direct fiber to your home. or you don't have a big telescope at your house, and installing that is something that would be really pretty expensive. Or if you're a soldier on the battlefield, you don't have either of those things. You don't have a fiber, you don't have some big telescope that you're going to set up. On the other hand, you could imagine having a portable one of these that would cost something like $5,000 or something like that. And in the morning, you would send your drone up, and it would find the central drone in town, and it would exchange enough key that would serve as the seed for the rest of the day, and then it would come back down. And so then you could actually imagine this being a much more applicable technology.
I'm wondering, is there any advantage or obstacle to, instead of mounting all of the sort of optics for sending and transmitting the messages onto the drone, sort of just using them as an a reflector?
A reflector, yes. So you could.
Across the
Yeah, so if I were going to do that, I would probably do that with a fiber tether. So I would probably send the signal up through a fiber. So polarization is a very bad option then, because as the fiber is moving in the wind, the polarization state's going to be jumping all over the place. So then instead you could do something with time bin encoding. And yes, there could be an advantage to that. We have to start somewhere, and certainly that does have the difficulty that now you have this fragile fiber hanging out, and that denial of service could happen by almost anything coming by, basically. So, right, I mentioned here that this kind of a network. It could be a model for eventually doing things with satellites, and there's certainly efforts in other places, and we have a small CubeSat project going on, eventually aimed at trying to set up some sort of a quantum network connecting all kinds of things, connecting telescopes by intermediate satellites, connecting CubeSats, connecting drones to other kind of platforms. So, okay, so that's going to allow me to transition going into space. So we could ask the question, what's great about space? Why should we care about this? And there's a really nice article that was written. It's almost a high-energy physics article because it's got like 30 authors on it. But a few years ago about different quantum optics experiments you could do with satellites and exploring a whole range of things, capitalizing on the fact that you have much larger distances and much higher velocities than you do on Earth. And that might enable new tests of fundamental physics in regimes that would be impossible otherwise. But also, the idea is that we might be able to then use that for enhancing applications of interest to NASA, for example, secure communication, distributed quantum computing, and I'll talk about some of these other things at the end. So one thing that you can do if you have a satellite, I mentioned that quantum key distribution requires a point-to-point connection, but maybe I don't have a point-to-point say, line of sight with the person I'm trying to communicate with. So let's say that I'm trying to do a communication with Ian back there, and we don't have a direct line of sight to each other. But instead, if we can at some point both see the same satellite, then we can do quantum encryption. So the way this is going to work, I'll play the role of Alice here, and Ian can play the role of Bob. So the satellite's above me. I generate a key of, say, 1,000 bits with the satellite. And then the satellite goes above Ian, and he generates another key that's also, say, 1,000 bits. And then the satellite, those keys are just random strings of zeros and ones, so they'll be different in about half the locations. And the satellite then simply radios down to Ian and says, OK, you should flip bit 1, bit 3, 5, and 6, bit 8, roughly half of the bits. And then if he does that, then he'll have the same key that I do, the same random string that I do. Now, because an eavesdropper didn't know the original bits that either I had or that Ian had, hearing flip bit number 2 doesn't give any information to the eavesdropper. So that doesn't ruin the security of the system. We do have to trust the satellite. So this is an example of a trusted node. And this is exactly the way the trusted nodes, I believe, in the Chinese network also work. Unless, as I say here, unless you use entanglement, in which case then the satellite can be made by your enemy, which I guess if you're in the Chinese link would be us or something like that. I don't know. OK. So there was a really nice review article last February in Optics and Photonics News highlighting or describing all of the quantum key distribution satellite missions that were either ongoing or planned. And you can kind of glance at this, and maybe someone can point out one interesting thing to me in this plot.
From the US.
There is nothing here in the US. There was well, there was nothing here, but when I was at Los Alamos, Richard Hughes and his group were working on developing satellite-based quantum key distribution. And someone who shall remain nameless in the government decided that was just not something that should be pursued at all. And so that got stopped. And if it hadn't been, then there would have been a different article which could have been written 13 years ago where there would have been just the US thing. Of course, then they wouldn't have written it probably. But OK, so we're now trying to become more invested in this area. And I'll talk about that in a second. Some of you may also be aware there was a huge milestone a couple years ago, 2 years ago, the Chinese Mikius satellite. I don't know what the correct pronunciation is. And it actually had several experiments that were done. So one of them was doing quantum key distribution from the satellite up. So this is basically this trusted node thing that we just talked about. Another one was distributing entangled photons to 2 ground stations. And then the third was doing quantum teleportation from ground to the satellite, although I'll come back to that in a minute and say not really, kind of, but not really. And then there was another experiment where they actually did a quantum link between not just these 2 ground stations in China, but going all the way to Vienna and making a connection there. OK, so that definitely generated a lot of interest around the world, I would say, which has been good for us, I guess. So I was contacted actually long before that and asked about trying to do some sort of quantum communication for NASA and what would be of interest. And the 2 things that you might immediately think of are quantum cryptography and teleportation. Now, quantum cryptography, I kind of crossed off the list as being too easy. So the eventual goal is to do some sort of a quantum network, not just to do quantum encryption. Because I think quantum encryption, as I mentioned, the US government is not that interested in it. And I personally, just for doing encryption and not, if that's the end game, I'm not personally that interested in that. I would rather have a quantum network, which could enable you to do a much wider range of applications. So you don't need to have entanglement in order to do quantum cryptography, so it's not necessarily a stepping stone towards some sort of a quantum network. So I'm going to cross that off as the main goal of our project for NASA. OK, teleportation. Teleportation has a difficulty in that it's actually, in some ways, maybe a little bit too hard. So just in case, to make sure we're all on the same page of how teleportation works, I prepare an entangled state. 1 photon goes to Alice. 1 photon goes to Bob. The unknown state comes from Charles. Alice makes a Bell state measurement on these 2 qubits on these 2 photons. She gets 1 of 4 results, which she transmits with 2 classical bits to Bob. He applies 1 of 4 transformations, unitary transformations, to this photon, and then he gets the identical to what Charles had sent by sending this 2 classical bits. Now, there are some challenges with this. In particular, with standard linear optics, you cannot do this Bell state measurement very effectively. You can only resolve 2 of the 4 states. That's proven. So that's a challenge. Also, you can see that it requires 3 photons. And so that's also a challenge just in terms of having high enough rates in this sort of experiment. And right, in order to really be useful, you sort of need to have this pre-distributed entanglement. So I would say we still need to demonstrate true teleportation from space to ground or from ground to space. So the Mikius satellite, they really demonstrated teleportation from ground to ground. Because if I look at what they did, they had this entangled source here. 1 went to Alice, 1 went to Bob. And then here's the unknown source that came, the unknown photon that came from another entangled source that went to Alice. But all of this stuff, this was all on the ground station. And then they just send the 1 photon up to the satellite. And then they just detect it. But if all you wanted to do was send this unknown photon up to the satellite, and you're willing to have all this stuff on the ground, well, you might as well have just sent this photon up to the satellite and not gone through the trouble of all this extra stuff in the middle. So it doesn't really buy you anything at all. What you really need to do is to be teleportation where the source is, say, on the satellite, and the unknown photon is on the ground station, or vice versa. And that's a much harder challenge. That's much more difficult that any kind of quantum network will have to face. OK, so the protocol that we decided to look at is this so-called superdense teleportation, which is going to be remotely preparing quantum information, but with some reduced resources, as I'll explain. And I want to make the connection with remote state preparation because it has some interesting connection with the topology of this quantum states. So in remote state preparation, we again have an entangled state that's distributed to Alice and Bob. In this case, Charles actually gets a hold. He has access to the photon before it gets to Alice, and he applies a unitary transformation on that. Alice makes a measurement on that photon, and then she sends classical information down to Bob, and then he does some unitary transformation to get out the state that is desired. But the way that this actually works, for example, if we're trying to remotely prepare a qubit, so Charles can make this unitary transformation, and Alice, she's going to have one of two possible outcomes. If she gets a 0, the bit that she sends to Bob is, don't do anything to the photon because it's in the state that you already want. And if instead she got a 1, which will happen the other 50% of the time, then the information she sends to Bob is, oh, the state that you got was exactly the wrong one. It's orthogonal to the one that you wanted that was supposed to be sent. And that turns out to be a problem, because it turns out there's no way to correct that. There's no way to correct this thing if it's exactly orthogonal, as I'll explain in just a second. So this kind of system can only be probabilistic. And in fact, if you go to a larger dimensional state, it gets less and less likely. So for a qubit, it's out of 50%. If you have a 4-level system, it becomes out of only 1 out of 4 times that it works. So the problem is that a qubit, of course, we can represent on a sphere, and there is no operation you can do that takes every point of a sphere to the opposite side of a point. So there's no allowed physical operation. You can do an anti-unitary operation, which does that kind of inversion, but there's no physically allowed operation because there's always points, the axis of rotation, that are not at all changed. That's different if you could have a different topology. So for example, if I had just a subset of this, just the equator, then you can do an operation that converts every state to its orthogonal state. Or if I have a torus, so a 3-dimensional version of this, now I have 2 phases, each of which go 0 to 2 pi. And if I wanted to do a complete universal knot, I just rotate my donut 180 degrees this way, and then I roll it in 180 degrees, and that has the operation that I want. So the point is, by working in a different sort of topology of the space, other operations become possible. OK, so now we're ready for superdense teleportation. So the idea is that Charles wants to remotely prepare a particularly stated Bob, but it's a particular type of state. It's what I'll call an equal modular state. So all of the terms have equal weight, although they can have random phases between them. And so in some sense, it's these continuous variables that describe these phases. That's what I'm trying to teleport from this side over to Bob. So the way that it works, let's say that he's trying to, is this particular state in mind with 3 phases that he's trying to send to Bob. Alice and Bob will start out with this 4-dimensional maximally entangled state. When Charles gets the photon, he will apply these phases to his photon. But of course, that applies the phases to the entire entangled state, because that's how entanglement works. It's a non-local state. He sends this photon on to Bob. She measures in a mutually unbiased basis, which is just a combination, linear combination of all of these basis states. And she gets one of 4 possible outcomes. She sends that information, 2 classical bits, down to Bob, and then he does a unitary transformation. And the transformation that he needs to do is he needs to put a minus sign on one of the 4 states, because it turns out, depending on which of the 4 measurements she gets, it's this state that Bob gets, except there's one minus sign sitting in one of the terms. So that's what that unitary transformation would be. And then at the end, he gets exactly the state that Charles was intending to send. So note that we're able to get 3 of these continuous phases for only 2 bits of classical information, whereas in teleportation, we got 2 of these continuous variables for the 2 classical bits. That's why it's called superdense teleportation, because you're getting more quantum information for the same amount of classical information. OK, so there are some advantages of why this could be good for a space project. So one is that it only requires 2 photons, not 3, so it's much less likely to loss in the system. So the source and detector requirements become much easier. We don't have to do this Bell state analysis, this very difficult 2-photon gate. You don't need as many classical resources. The space itself is kind of interesting. And it does enable you to do other interesting things like higher dimensional quantum cryptography, novel tests of non-locality, and it's also a resource for so-called blind quantum computing. And I'll talk about that at the end. So the implementation of this in our laboratory, although this is also notionally what we're thinking about for the space station, is that we have the entangled source on the space station, and then we send these photons down to Bob. Now, we need to make this higher dimensional entangled state, and the way that we'll do that is by using multiple degrees of freedom of our photons. So we'll use both polarization and timing. So we need to make a state that is entangled in both the polarization and the timing degrees of freedom. The way that we make this is we have a nonlinear crystal, and when we pump it with a 532 nanometer laser, sometimes those photons split into both an 810 nanometer photon and a 1550 nanometer photon. That conserves energy. And that happens in this particular crystal here, this periodically poled lithium niobate nonlinear crystal. And if the pump that's giving rise to this pair is born in this Sagnac interferometer by going around clockwise, then we produce two horizontally polarized pairs. And if it's produced by going around counterclockwise, then we produce two vertically polarized pairs. I think I got those backwards, but anyway, we can make this polarization entangled state. We can also make the time bin entangled state just by splitting the pump, every pump pulse, into two different time bins, just with a simple interferometer. And then for his part, Charles induces these phases, phi 1, phi 2, and phi 3, by using some liquid crystals that are in the beam. And then Alice and Bob both have unbalanced interferometers and some other polarization analysis to enable them to carry out the rest of the protocol. OK, so this is the obligatory picture of the full state tomography of the whole thing, this rather large dimensional space, with a reasonably good fidelity to sort of the perfect state that you would want, this perfect 0, 0 plus 1, 1 plus 2, 2 plus 3, 3. And actually, we're underway to push that up even a couple more percentage points. I think that's pretty likely. We've also done this superdense teleportation protocol. So for example, this is the state when Alice gets a click on her A1 detector. Then this is the state that Bob should be receiving. There's a minus sign on one of these terms. And if instead it was the A2 detector, the minus sign would be here, for example. So this is the measured tomography that Bob has made conditional on Alice's A1 detector. And these are the states that we were trying to send, the phases we were trying to send. This is what we actually were able to send. So we have a fidelity of order 94, 95% in this case. And we've examined pretty much the whole state space by doing measurements every 45 degrees in all three parameters, phi 1, phi 2, and phi 3, with an average fidelity of about 94%. And an uncertainty in phase of something of order 9 degrees. So with this system, we can make and resolve about 10,000 individual states. OK. I mentioned tests of non-locality. So we did some Bell tests on this. So I don't really want to go into detail on these, but we make certain correlation measurements and coincidences, and any classical system that obeys locality and reality would have these correlations bounded by 2. Quantum mechanically, you should be able to get up to 2 root 2. And we can show that both our polarization and our time bin qubits exceed this bound of 2. That's indicating that there are no local hidden variables for those particular degrees of freedom. But maybe you want to do something more general where you're combining all the degrees of freedom. Is there anything interesting that you can do there? And the answer is yes. There are these more sophisticated Bell inequalities which involve not just 2 measurements on each side and 2 outcomes on each side, but higher numbers of measurements or higher numbers of outcomes. So this I222 is just the normal Bell inequality that I just showed you. But there's another one where you have 4 measurements on each side. And if any local realistic theory is bounded that this I, which I'm not going to show what the inequality is. It's not that illuminating to look at it. But it should be less than 0 for any local realistic model. And you can violate that with qubits. But in fact, if you have higher dimensional states, you can violate it by more than you could with qubits. So in particular, with this equal modular input state, qubits can get a value only up to about 0.18. Whereas with this equal modular state, we should be able to get up, that we can make in our system up to about 0.46, and that's more or less what we've been able to see in the experiment. Okay, we've also been able to do higher dimensional quantum cryptography. So we can do standard quantum cryptography just using polarization. So we've been able to do that with relatively low error rates. The other thing, once we have this larger dimensional space, is you can also do cryptography where you get more than 1 bit of randomness per photon. So in this case, we only get 1 bit of randomness per photon. But here, because I have 4 different possible outcomes, and Alice and Bob say if they measure in this logical basis 0, 1, 2, 3, they'll always get the same result. Now that means they get up to 2 bits of key per photon. And again, we've been able to have fairly low error rates. One reason that that might be of interest is that this sort of a system can actually tolerate much higher error rates. And in principle, because you're getting more entropy per photon out of it, there are regimes in which you can get a secure key in this case where you can't get a secure key in this case. So that could be, and it's quite possible that in a space experiment, because we don't have very high rates, quite possible we might be in that regime. Okay, and in fact, that's just what this is showing, that if you can use this higher dimensional case, you can get more key out. And there are situations where you can get key in the 4-dimensional case where you really can't get any key just using qubits. Okay, so what makes this challenging? I mean, we've obviously done this in our laboratory. So we'd like to do this on the space station. And it would, for example, sit in one of these outer bins on the space station. And we can calculate, or rather people from JPL can calculate for us, or Lincoln Lab can calculate for us, how many times will we actually see the space station in a given year, and how long will those durations be? It really depends whether or not it's going straight overhead where you have a long time, or whether it's going just barely over the horizon where you don't really have much time. And so this is just a plot of what you can expect. And basically, let's just say that we expect to have something like 1,000 passes in a year. That, of course, doesn't guarantee that it's good weather or anything like that. And they'll be of the order of a couple minutes, a few minutes. So one question you might have, well, it would be, well, OK, will you actually have enough time to accumulate enough data to do a tomography or to verify any of these states, for example? And so we just did a measurement of, by varying the total number of counts we were using for doing our state tomography and showing that, OK, if we can get more than about 100 or 500 total counts, then we really can get a fidelity that's starting to saturate. And our error rate in our phase is also starting to approach a minimum here, is starting to asymptote. And so that's needing roughly 1,000. And we believe that we should be able to, in a typical ISS pass, get something like 4,000 to 10,000 photons a second. So that should be feasible. Another problem that you have that doesn't exist in the laboratory is the effect of the fact that the space station is moving, and it's moving very quickly. So it's moving at about 7 kilometers a second. And if you think about the fact that on the source, we're producing these 2 time bins, and then on the ground, we're basically trying to interfere them. We're trying to interfere the fact that the photon that was born early took the long path, with the photon that was born late took the short path. The problem is that when the space station is coming towards you, of course, those are Doppler shifted together. And when it's moving away from you, those are Doppler shifted apart. And it's not a small correction. It's a correction of order, in terms of like the separation of these, something like 20 micron shift. And that corresponds to a phase uncertainty or a phase change of something like 26 pi, whereas we'd like to do interferometry where this is stable to like a degree of phase. So that's going to be tricky. So we've we've simulated this basically by having an interferometer that mimics exactly what that 20 micron change is, and then put in an active stabilization system in all the interferometers that can correct for that to within about a degree of phase. And this is just showing, for example, doing quantum cryptography where you don't have the stabilization, where at least one of the error rates that depends on that relative phase is very high. And with the stabilization on, the error rate is kept to a manageable level. OK. Where do we go from here? So we already have hyperentanglement, and we've demonstrated superdense teleportation and quantum key distribution in our laboratory. So that certainly is something that should be pretty possible. One application of this could be for so-called blind or cloud quantum computing. And let me just talk for a second about what that is. So let's say that Google eventually makes their quantum computer, but they're the only one that has one, or Intel, or whoever your favorite, Rigetti, whoever your favorite quantum computing company is. But there's only one, and it's not close to you. But you have this amazing protocol. You want to simulate this molecule that's going to revolutionize how we get energy from plants or something like that. So you have a couple choices. One is you send your program to the owners to run it, and you tell them to tell us the answer, but don't look at what the answer is. You're maybe not going to be too anxious to do that. Two, maybe you have a local agent, and then you can send over the information by quantum cryptography to that local agent. The third version is that you will send the program encoded in particular quantum states that only you know, and then there's a process. Then the computer on the end processes those quantum states, returns the answer to us, but because we're the only ones who know how they were encoded, we're the only ones who know what that means. And that's so-called delegated quantum computing, or you might think of it as cloud quantum computing. And it turns out that the states that you need to do this are exactly the equimodular states that I talked about. And in fact, there was a simple demonstration of this back in 2012 by Anton Zeilinger and Philip Wolter's group. So that certainly seems feasible. What else? Well, as I mentioned, we'd like to do full Bell state analysis, entanglement swapping. That could lead to quantum repeaters. And that could lead to either distributed quantum processing, or the other thing that people have talked about is distributed quantum sensing. And that's the last thing I want to talk about for 1 minute, because it's a rather interesting paper that has been now shown at many workshops that I've been at for why one really wants a quantum network, or why one might want it. So it's this paper by Gottesman, Yenevayan, and Croce. And the idea is that if you have a telescope, the angular resolution of a telescope is limited by the diameter of the telescope. The bigger the diameter of the telescope, the better the resolution. But you can't make a telescope that is, a kilometer across, because you can't. It's just too much material. And certainly on ground, there would be too much turbulence. So instead, you could take two smaller telescopes, and if you can bring the optical signal from those two telescopes together and basically do an interference measurement of them, then you can get the resolution that's then limited by the separation of these two telescopes. And that's basically how radio telescopes work. It's very long baseline interferometry. It's not that easy to do optically, though. It's easy enough to do in the radio because the wavelengths are long, and so they can do that. But in the optical, you're sort of limited in practice to something like maybe 100 meters or a kilometer at most. People haven't been able to do better than that. And so the idea of this paper is that you could instead use quantum teleportation, basically, to teleport this rare photon that comes in, to teleport it to the other side. And in that way, you would basically have a lossless channel. OK, so it turns out there's a lot of things that make this very difficult. So this is not going to happen anytime soon, and maybe never. I've put it in the 50-year category, where I'm saying that because I know that 50 years ago, we had no internet, no cell phones, and we just couldn't imagine. So you really need to have lots of entangled photons. It's not easy. But if you could do this, what would that enable you to do? So let's say you're looking at some distant exoplanet, and with standard very long baseline interferometry with a wavelength of 1 micron, and you can get maybe your telescopes to be 100 meters across, so that gives an angular resolution of 10 to the minus 8. If instead you could do this with your quantum enhanced very long baseline interferometry, and this were 100 kilometers, maybe telescopes on either side of the planet orbiting it or something like that, then you get a much better resolution, and then you could really start seeing interesting things. I mean, you could definitely be able to look at for cities on exoplanets or something like that, other kind of features, which otherwise would be completely impossible. OK, so setting something like this up is very difficult, but certainly could enable you things that I guess I don't know any other way that you could possibly do it. OK, so in summary, I've shown that I think we're pretty close to having this portable quantum key distribution systems that could lead to other applications, not just for QKD, but for doing small-scale entanglement distribution. We've been able to implement the superdense teleportation protocol with reasonably high fidelity, and shown that we can tolerate the losses that we expect to have in a space station platform, and been able to use that for demonstrating quantum key distribution. So in answer to the question that I started with, where do we go from here? Quote Buzz Lightyear and say to infinity and beyond. Let me say that getting something up in space is a rather expensive venture. of order $100 million or something like that in order to fly an experiment like this. So that's a bit of a lift. But I am encouraged because I believe that this could be our new spokesperson as part of the Quantum Space Force as a way of being competitive and maintaining our quantum dominance over the rest of the planet. OK, probably not. But thank you. Thanks for your attention.
Questions?
With regards to the drone-based thing,
Yep.
I guess it's extremely difficult to send to lock in a channel between them.
I think we will have it. I think we will have it working.
I just wanted if you could comment on how realistic would it be for an eavesdropper to, if you were sending a classical channel, you could probably monitor power fluctuations if there was an eavesdropper. I guess a classical eavesdropper would be extremely hard for it.
Yeah, I don't think it's as hard as you may think. So let's take the case where we're going close to, we're 30 kilometers apart, so the two ships aren't, maybe they don't see each other all that well, but you're coming pretty close to the surface of the water. So I can imagine, I have not thought about this till this instant, but I can imagine a submarine coming up from below and lifting a piece of saran wrap that deflects off a couple % of the beam off. And it could be pretty hard to see, but it would still take off some small percentage of the beam. And if it's a classical signal, that would certainly be readable. And it could be quite difficult to detect those fluctuations at the couple % level.
Right.
Yeah, here. This way.
So in the Komarov model of turbulence, right?
Yes.
The phase distortion goes 1 over the wavelength squared.
Yes.
So is there a reason why you're using an optical light of this wavelength that's kind of very short? If you use a long wavelength, cannot get this phase distortion?
Yeah, that's a very good question. So it absolutely is true that if you went to much longer wavelengths, even like 4 microns, it turns out then you can go right through fog, and that's like super great. The problem is it's very difficult to detect single photons lightly, where by lightly I mean in a low mass system. So we can detect infrared photons efficiently, for example, with superconducting detectors, but that is a system that I can't fly on a drone that we have access to. Now, if you use a tether coming down, then that is something you might be able to do, but again, that's not something, if you think about a practical application, you don't necessarily want in your home to have superconducting detectors. So at the moment, we're choosing the optical ones because you can get nice, small light detectors, but that doesn't mean that there aren't advantages to doing longer wavelengths. Let me just answer the other question that you didn't ask. But on the space thing, you might ask, well, why are you sending down with long wavelengths instead of short wavelengths? Because then diffraction, it hurts you more. And that's because NASA said, we already have all this technology developed because they're developing optical communication links, and they're developing it with telecom components, and they don't want to look at doing anything other than optical, than telecom wavelengths. So we stick with that for now.
It's actually a very similar question.
OK, I can give a very similar answer or a totally different one, as you like.
Have you thought about going to larger alphabets rather than just 0, 1, 2, 3 that you were showing in the few days?
1, 2, 3, 4, yeah. We certainly could by using, for example, more time bins or something like that. It turns out that the measurements start to get more and more difficult in terms of doing the mutually unbiased basis measurements. And it doesn't seem like it really helps you enough to make it worthwhile. And it also then becomes harder and harder to do all the stabilization of things. You could also do spatial mode encoding, but not if you're going to go through turbulence. So that might work if you're going to go in outer space. But no, it doesn't really work in outer space either because the higher order modes diffract more quickly, so they experience a lot more loss. So it seems to be good at the moment for us to stick with something fairly small.
Frequency?
In principle, one could do frequency. Of course, there's a reciprocal relationship or conjugate relationship between frequency and timing. So the thing with frequency is that you then have to have nonlinear effects in order to make superpositions of different frequencies. But for example, Andrew Weiner at Purdue has been looking at exactly that sort of thing as a possibility. And it certainly for the space project, it still has difficulty that then the Doppler shift starts to hurt you.
Related to that, to go to higher dimensionality with the superdense coding, what's the scaling when you go beyond 4 states?
The scaling in what regard?
In the increased density of coding.
the number of states that you sent, so however many terms you had, 0, 0 plus 1, 1 plus 2, 2, the number of possible measurements that Alice will have is just that number of states. Because one of those terms will have a minus sign, and she just has to send back where the minus sign is. So it actually scales better than teleportation. In asymptotic limit, it's a factor of 2 better than teleportation. So you need half, in the asymptotic limit, a very large dimension, you need half as much classical information for the same amount of quantum information.
Have you thought of doing superdense coding with more dimensionality?
Well, I think this is sort of the question that she was, did you come to the meeting or what? No, she was saying that I was saying that it's not that easy. It's not as easy to go to much larger spaces, and it doesn't necessarily seem that there's a benefit at the moment. I will say one other kind of acute thing, which is that if you compare a qubit to a slightly smaller space, so if I take a normal, well, you guys know what a qubit looks like, so if instead I just take there, this one. So this has two parameters, just like a qubit has 2 parameters, right? Cosine theta 0 plus sine theta e to the I5 1, right? This space is actually a little bigger than the qubit space because each of these parameters goes 0 to 2 pi. And on the qubit case, only one of the parameters goes 0 to 2 pi and the other one goes 0 to pi. So actually, in an earlier paper that we did with a mathematician, he did some estimates of how many states, if you could have a certain minimum size that you could resolve, how many states you could pack into that higher dimensional, that hypertorus. And it turns out you can pack more states into the hypertorus than into the equivalent qubit type space. Although there's some assumptions there because it turns out people have not solved the packing problem. It's certainly not in higher dimensional hypertoroidal spaces. Yes.
Back to the drone project, would you be happier right now if you had just used balloons that could just hang up there and, yeah.
Good question. So the original proposal we had was for balloons, actually. And the reason I didn't like that is that it's not so easy to do things very quickly with a balloon. And then it becomes, denial of service can become really pretty easy if someone just cuts your tether and whoop, and then the balloon is completely gone.
That's right. But it's easier. I mean, you switch off to a drone later on in the project. Or
yeah, well, I don't know. I feel like if the outdoor movie I just showed you, if I said, and when they're in the air, they're doing quantum communication, which I'm hoping we'll be able to say in like 2 months' time. That just is a lot cooler than just having 2 balloons that are sitting up there. Well, it's marketing, but it's also something you could imagine if you're on a battlefield or something like that. The soldier sends his drone up, it exchanges things, and it comes back down. It's not a target that's sitting up there for large amounts of time.
Yeah.
So on each of the drones, you have a transceiver, the transceiver and the receiver?
At the moment, we just have a transmitter drone and a receiver drone. If you want to set up this more complicated network, then you have to do both on one. And that's something we can think about doing a couple years from now once we get the simpler version going.
So, why did you choose BB84 over B92 for this drone project? Isn't B92 easier than
It is, but the problem with B92 is that you have to kind of keep track of the losses in your system, right? So you're only secure if you know. So it's been a while since I thought about B92, although I did think about it a lot when I was at Los Alamos, and you have to. An eavesdropper can come in and can spoof you a little bit in B92. She'll affect the loss of the channel, but that means you really have to monitor the loss of the channel. But if you saw even with the stabilization on, there's quite a large variations in the loss of the channel. So I think it's easier to do it this way. Yeah, I guess that's all I'll say on that.
Is there like a simple reason why Fibonacci states are ideal for blind quantum computation?
I have no idea. I would love to have a deeper understanding of that. And I mean, I know how they're used for it. It's with a cluster state model. If you look at the paper, that's pretty much the only way people have come up with, as far as I know, to do this delegated quantum computing. But I don't really have a deep understanding of why it turns out that they're sufficient. Which is interesting because they are not sufficient to do arbitrary, as far as I know, they're not sufficient to do arbitrary quantum computing. Because you can't convert an equal modular state with 4 terms into, for example, 2 qubit states. Yeah, there's no unitary transformation that goes between. Obviously, if you could convert them into qubits, then you could just do normal qubit processing on them. But as far as I know, you can't do that conversion.
No more questions. Let's thank Paul. And,
Thank you so much.
there will be the 4 o'clock tea.
Please.
Really sick suspenders, by the way. They look really
Oh,
cool.
thank you. Paul, while they keep my pants up. I'm sorry, what's your name?
Andrew.
Hi, Andrew.